So we will start here now with a bit of the first introduction to the map, just being a layer explainer. What are you actually seeing when you go onto the AREMI site, which is www.nationalmap.gov.au /renewables. And when you start, you'll actually get a disclaimer the first time you use the maps, which basically says this data is indicative and provided for the benefit of the market, but not to solely base investment decisions on this alone, but rather to use it as a starting point to inform your development of opportunities as a starting point for conversation with the network business. And that's really how our data suppliers view the network opportunity map as a lubricator of the relationship between the market and network businesses. So this is the most recent addition, the Generation Connection Opportunities Map, the most recent addition to the NOM family, thanks to our key partners Arena, AusNet Services, PowerLink, Transgrid and Data61 for their fantastic work on the development. This is the first time anyone has seen it. This map shows the indicative capacity that the existing network has to handle the connection of new generation. So this is information that would generally be obtained via an initial connection inquiry process that could take weeks or months and might result in a community group or a renewable energy developer completely rethinking at what scale or where they actually site their generator. So this new layer really provides that first pass information up front, making things faster and easier for both the proponent and the network business as well. And in addition to our core partners for this layer, huge thanks to our data suppliers. What you're looking at on this map, you also have Victorian transmission data from AEMO, we have ActuAGL, PowerCore, Electronet, and Essential Energy, is what you're seeing here in this zoomed out version. So let's just zoom in a little bit to a New South Wales view where we see a mix of Transgrid, Essential, and ActuAGL data. So the dots that you see here are substations. They're transmission, sub-transmission, or distribution zone substations, and the lines that you see are sub-transmission lines. So they are all color-coded according to this legend over here on the left. You can see the laser pointer over here on the left. And so where there's the blue are large amounts of available capacity in sort of the hundreds or thousands of megawatts, and the orange and red being relatively little available connection capacity in sort of the ballpark of 0 to 5 megawatts. And the key thing with this layer is that network businesses needed to have it updated on demand rather than annually. So it's managed via an online upload platform that publishes directly to the maps once the business hits approve. So that if a 10 megawatt solar farm is committed this week, then that's the data that you see as a user can quickly reflect that. So if you click on any asset, you will see a range of information. You'll see what it is, its voltage level. In this case for Dubbo West, that the indicative available capacity is about 23 megawatts in this circumstance. And we can also see that this figure accounts for thermal limitations only. And it doesn't actually consider voltage and stability considerations, which might be assessed in a later, more detailed assessment. So each business that provides data actually uses their own methodology, which might consider different factors. Some businesses consider all of those factors, others only consider thermal, and it's all laid out for you here in the info boxes. Okay, so the next map we have is available distribution capacity. So what you're looking at here is a whole series of polygons, and those polygons are the distribution zone substation region service boundaries. So what this map shows is the capacity of the existing network assets at the zone substation level to be able to meet forecast load growth over the coming decade. So, and I've said the coming decade, what you can actually see, note my laser pointer here, is down the bottom, there's actually a time slider. So the map that we're actually viewing in this slide is 2025, out here in the future. But if you click on any point during this timeline, you can get a different picture of what the circumstance is in that at that particular time. So what available capacity is pretty simple. It's just the current zone substation capacity minus the forecast peak demand. And what you're looking at here are the green areas where there's sufficient capacity and the red areas where there's a capacity shortage and an impending need to do something about it. So these are the areas that will need either network augmentation or demand management to actually alleviate that constraint. So there's actually constraints at a whole number of different levels of the network. This is just zone substation information, and they're generally not represented below that level. However, AusNet have actually experimented with this year, showing distribution feeder level shapes, and I'll show you this a little later in the live demo. Really, the observations in this map is quite similar to last year's data, which show a lot less red than you would have seen in this map 5 years ago, because of owing to relatively recent investments in new network capacity at a time when load forecasts that started to taper off. And the exceptions here are some residential growth corridors around our major cities, and also in Victoria, which is where you see this sort of red patch down here, where there's probabilistic planning criteria that apply an asset to run harder under higher load before an augmentation is made. Now we've got our proposed investment map. So this layer shows the locations of proposed investment to meet these impending constraints. So this layer covers augmentation, but it also includes replacement and refurbishment. And this year, users are actually able to select the display variable, and there's a whole bunch of different choices you can make. This was not previously possible. It's one of the new features. So the default is the year of investment. So you can see that the red investments are the ones that are imminent and about to occur. The green ones are sometime out into the future. But you can also specify to view by asset type to determine what transmission, what zone substation, what feeder. You can look at the constraint season, whether or not it's summer or winter peaking or both. You can look at the investment driver, be it augmentation or replacement, and when you click a particular asset, you'll find a whole bunch of information about it here, which is, I think, the largest augmentation investment in the data set this year. We've seen Electronet $200 million transmission line with $120 million of that specified as deferrable. So that's happening in 2022, but there's a commitment year that you can see quite soon in 2018. So there's often some more detailed information about the constraint in this box as well. It depends on the network business. And the final and perhaps most useful one of all of these is deferrable investment. So this is where the network specifies what's deferrable or avoidable, and it will, if you click this, it will actually grey out if it's not deferrable, and so you can quickly see the investments for which non-network alternatives present potential money on the table. Now, our next one then combines the load situation that you saw in the first map and the investment situation that you saw in the second map to create what is our key opportunity hotspot layer, called annual deferral value. So this shows what it's worth to connect, what it's worth to the network to defer that investment for a given year. So to do that, we take the proposed network, or the deferrable component of the proposed network investment. We take the weighted average cost of capital, so the interest that would have accrued on financing that asset, and the avoided depreciation that wasn't incurred from an asset that's not yet built. And you put those things together and you get an annual value of deferring augmentation in sort of dollars per year. But then we actually have to think about how much work is required to actually achieve that deferral. So we divide that by the non-network support requirements in each year in kVA terms. And so we get this annual deferral value, which is a marginal value per kVA of avoided growth. So dollars per kVA per year, if that deferral is successfully achieved. Now, this is what that map actually looks like. So this is the area of Greater Sydney. And so you can see the legends over the side here, where you've got white and yellow areas are relatively low values, and your reds and purples are quite high values in dollars per kVA, up sort of around the $500 per kVA per year mark. And what this is not what the network is willing to pay for demand management, but it shows you the marginal cost of the preferred network option, which gives you an indication of the upper limit that the network business could invest in demand management and still save money. So, and this one is also a data set that has 10 years worth of information in it. So down here on the bottom, we have the time slider. This particular image is about 2021, as you can see what's selected near my marker there. So the value that you see in these maps is mapped to the zone substation areas. It also includes the value of upstream transmission and sub-transmission deferrals that are then passed down to the areas in which demand management could be effective, that are actually connected to that upstream asset. So in the case here of Sydney, we actually see a whole bunch of zones in the inner city area that I'm circling here. And those all actually have the same colour, and the reason for that is that they all relate to Transgrid powering Sydney's future project. And so demand management can be equally effective if applied in any of those connected downstream zones. So you actually sort of see the value stack of any distribution, of any sort of zone substation, any sub-transmission, any transmission, all added together in this map. And this is the information that you get when you click on any particular asset, where you will see the annual deferral value and the amount of support required in any given year to achieve that, which is both tabular and the new graphing features that Data 61 has added as well. So the question is, these values are all very nice in dollars per kVA per year, but how do you actually use it? How do you apply the annual deferral value? I'll just give you a quick example. So say there was a $10 million network investment driven by a commercial cooling summer peak constraint at 2 in the afternoon. It requires 2.5 MVA per year of non-network support to actually be able to achieve that deferral. And so in this case, say the value on the map is $400 per kVA per year. And the proponent in this zone substation area is looking at developing a 3 MVA gas trigeneration system, which delivers 3 MVA of electrical generation, as well as 0.75 MVA of an offset to cooling demand within the building. And so you get 3.75 MVA summer afternoon peak reduction, so which could plausibly achieve a 1.5-year deferral of that asset. So the way you apply it is to say, okay, let's take that $400 per kVA per year, multiply it by 2,500 kVA, so the amount of support required, by 1.5 years. And so when you multiply that out, you get a total value of $1.5 million. And that's essentially, that means that firm generation of this scale is worth up to $1.5 million to the network business. So the network business will want to actually have a more efficient solution than the network option, so they'll want to spend less than this amount, and they'll also run it through a competitive process, meaning they get the best value outcome with the lowest possible cost of distributed energy options. But this just gives you an indication that you could then, that this generator might want to start factoring in a possible value stream of between, say, $500,000 and 1.5 million or thereabouts of a network revenue stream if it was to want to enter into contract with the network to deliver that supply. Now, our final map is peak day available capacity. So our augmentation investments in the network are undertaken to avoid peak demand reaching capacity of network infrastructure, but that tends to only happen for a few hours a year. And so it's actually really useful to show the timing and the magnitude of the constrained hours on the peak day. So if, say, a user has identified a particular annual deferral value opportunity that they want to dig further into, this map layer shows the percentage of capacity. So you can see in the legend over here, or that could also be termed the asset utilization for each hour of the locally relevant peak day. So in some zones, you might be looking at a summer peak day, and in some zones, you might be looking at a winter peak day. And this layer also has a time slider down here, but it's not for 10 years this time, it's for 24 hours from midnight to midnight. So you've got, we can see this particular slice, we have selected 5 p.m. So anything that is red here has an area that's exceeding capacity at 5 p.m. and those in green are not. And when you click on any given zone, you get a whole host of information and a really nice peak day load graph. And so you can really just navigate around here and see the peak day load shape of any of these assets in the national electricity market, which has never been possible in such an easy way before.